part. And okay, so this is about the connection between extreme value theory and dynamical system. And let me tell you, before going to the slides, let me tell you something about the general philosophy which is behind what I'm trying to do, just to apply some statistical properties of a dynamical system to extreme value theory. So the extreme value theory basically is, at the beginning, is just a pure probabilistic theory. So you have some sort of, you have a process here, an IID process, with some probability p, which gives the same distribution for all the variables here. And when we move to dynamical system, so this is the pure probabilistic setting. I will be more precise later on, just to show you what one can do. But in some sense, Tobias already spoke this morning about general aspects of this theory. When one wants to move to dynamical systems, so basically the process here will be some observable computed with the dynamics, and the probability will be the invariant measure which allows the system, and the basic observable which we used up to now, because now people are changing the observable, as Tobias said this morning, which we used is this kind of observable. So this is the initial condition which I put here, is minus the log of the distance, if you are in a metric space, between your point and some point z. And basically, when you look at these events here coincides when you take this kind of observable with the measure of a ball which has center in z and a radius e minus u. So these two events are equal when we study this kind of observable. So you see, since here you have the measure of a ball which has center z, some radius e minus u, which I call simply rho, the idea is if this measure, the measure of this ball scales like rho with some exponent d, which is a sort of local dimension, the idea is to use the universal three laws which are connected to the extreme value theory just to get this number here. What Tobias said this morning about experiments on some low-dimensional dynamical system in order to get this dimension d. The point here is, if we want to do a mathematical theory, we need to precise what this symbol means. And the point is, in order to get rigorous result, we need just asymptotic developments of this measure, just to get this is rho, just to get this kind of scaling. And as far as I know, there are no rigorous results, but mu is a Lebesgue measure. In this case, everything is more or less trivial. Okay, so now let's move to another situation, which is the situation where we put more probability on the dynamical system, and we consider random dynamical system. Okay, there are several ways to perturb randomly a dynamical system. I will show you in a moment at least two. The idea now is to consider new sequence of variables where we still put the alia on the initial condition, but we put something else now, some other variable omega, and basically we wrote this as an observable again, and now I take here Tn omega is a sequence of, it's a concatenation of maps which are each one close to the other, and the way I choose this map will be according to some distribution which allow me to choose this omega here. So we have the randomness on the choice of the initial condition and on the choice of the map. And in this case, the probability usually will be the direct product between the stationary measure, which takes care of the initial condition, times the measure on the noise. And the idea is, again, to use this kind of framework to say something about the local scaling of this measure here. But the point is that this measure here, as soon as we put a noise which is smooth, for example, absolutely continuous with respect to Lebesgue, this measure here is also smooth. So we don't have new properties about the fractal structure of this measure. This is the situation. But then with Davide, we discovered that if we use some kind of random perturbation of a dynamical system, which is, by the way, probably the easiest way to perturb a dynamical system, namely to use what people call observational noise, one could try to come back to this framework here and to get some information on the environment measure here, and to try to make this more precise, because I will show you, we have not to go to the limit with the radius, but just to stop with a finite value of the noise. Okay, so this is more or less the general setting I'm trying to show you. Okay, so this is just the first paper I will speak about with Davide, and he will speak about application of what we did in the next talk. And this is probably, I think it's interesting for you, because this theory has been applied to some physical situation like related to climate and meteorological issues. Okay, so the observational noise is really very simple. Basically, you have your map, and instead of taking the iterus of a point x, you take the iterus of the point x, and when you arrive to some point, you add some noise. Epsilon is the strength of the noise. Okay, so this has been studied even by strong probability guy like Lale and Nobel, and they wrote here that this noise is for several reasons is important. For instance, with this kind of noise, you can simulate the round of error when you do numerical simulation, for instance. And that is a little bit different from what usually people do using randomness in the dynamical system, namely what is called random transformation. I will show you in a moment what random transformation are. Okay, so now we are interested in this kind of noise. And okay, this is some sentence about the interest of this noise. And okay, some other points related to the interest still of this kind of perturbation. Okay, when I did this talk a few months ago in Leipzig, Kiefer told me that this noise probably is not very different from the random transformation noise. So this is one more interested to study this kind of perturbation. Now there are some algorithms which allow you to filter this kind of observational noise in order to get the true dynamics which is behind it. And finally, recently, and this is the reason why I began to be interested in this kind of stuff, I don't know how to prove the concentration inequalities for this kind of noise. Okay, our goal, I already told you what is, so it's not, let's go further. Okay, so what are the systems? So let me first of all spoke about the system and then about the noise. So the system is basically the system everyone would like to have when one works in dynamical system. So it's an expanding map, so non-invertible expanding map, and some compact manifold which preserve some measure mu, which I will take equivalent to Lebesgue because I want to apply the spectral theory, and so on and so forth. And okay, the reason we use this kind of easy system is not because it's easy to prove it, because it's very complicated when we go to more difficult systems immediately. And probably even a lot of stuff are not even true. Anyway, the most important technical fact here, which allows us to get the proof, is the fact that we have the curve correlation. We have the curve correlations where one of the two observable is L1. This is very important for some reason. And okay, and then okay, things, for instance, to map of the interval where one function is the bounded space of bounded variation function, and the other one is in L1. This is the prototype of the system which we have in mind. And then about the noise. Where is the point? Okay, this one. No. Okay. Anyway, about the noise will be a smooth one. So we take. Okay. Anyway, I wanted to use the red stuff, but I don't know where it is.
In the middle of the button.
Okay, here. Okay. Yes. Okay, so okay, this is the kind of noise which I'm going to use. So I told you before we had some noise at each step, and we took this noise as a sequence because at each step we put some noise. So this also a sequence of IID variables. It is important, the variable IID, and also independent with respect to the choice of the point. And we take this variable distributed smoothly around the point where we arrive. And all of these values will have, of course, the same distributions. So the observational noise, one more time, is defined here. And again, I take this kind of observable, which is the observable which I told you before. And this kind of observable was first introduced by Pierre Collet for some, for evident reasons, because, thanks to this equivalence, this observable here, this event here, when you take this observable, you construct this event is exactly equal to this one. And so if you look at this kind of events, especially to the second one, the statistical property which are related to this event here are the statistic of returns in some ball. And so, and this was studied recently, by several people in the last 20 years. So there was some reason to introduce this kind of observable. And now we discovered also the interest of looking to these local dimensions. Okay, anyway, this is the kind of observable which we are going to use. And now, okay, this is the process. So we take the observable and you compute the observable along this orbit, which is perturbed in this way, using this kind of noise. And the probability which we put, which will be the probability on the probability space which we are going to construct, is exactly the product between the invariant measure. So we don't have the notion of stationary measure because there's no any Markov chain structure related to the noise, but it's just the invariant measure time the measure on the noise. And what is important to remark is the fact that we put the noise even to perturb the initial condition at the beginning makes this probability stationary. That is important for the following, because this theory works for stationary process. And okay, so what is EVT, EVL or EVT? Just a few more remarks with respect to what Tobias said this morning. In a more general framework, to study this statistic of extreme value means the following. So you have some m variable, and suppose this variable are IED for the moment. And okay, so you look at the maximum, and then you look at distribution of the maximum. The point is, if you do not normalize suitably this distribution, you will get some degenerate. Of course, it's very trivial to prove you have some degenerate asymptotic distribution. So we have to normalize. And I will tell you in a moment what UM is. But suppose for the moment, we have to normalize in order to get something which is not trivial. Okay, and then you have to prove the following. I mean, you say that you have this kind of statistic if, having fixed a tau, positive number, you can find a sequence, UM. You remember UM is the normalizing factor which you put here, which depend on tau, such that whenever this limit exists, so whenever this one exists, you have the next one. I will show you in a moment why this is natural in some sense. Okay, so this is a very general framework for this kind of theory. Now let me explain you why one came to this kind of abstract formulation, which is not natural at the beginning, but it will become very natural now, because okay, suppose you have IID, okay, and then suppose we have the previous scaling, which is wait a moment, which is this one, okay. This is the assumption now. Suppose we have this kind of scale, asymptotic scaling when I go to infinity. Yeah. So now, if the variables are independent, okay, the probability that the maximum is less than or equal to UM means all the variables are less or equal to UM. So you factorize and you get this kind of quantity. And since due to the assumption which we put on the distribution of x0 bigger than UM, we get this one. So we go to the exponential. And so in this case, the asymptotic law is just the exponential one. Okay, so you see, in some sense, it's natural. And now the point is why people usually put some sort of normalization on UM. Okay, there are two reasons. The first one is because we can find 3 universal laws, as Tobias said this morning. And according to me, there is one other reason, which is probably more deeper, which is the following one, which is a theorem by Kinchin, which already Tobias announced this morning. But it seems to me you have to stress this result, because the result tells you the following. Okay, suppose we want to prove this, Mn less or equal to, for instance, I'm sorry, let me write in this way, Am time mm minus Bm less than y. suppose this goes to some gy, okay? And then suppose you have another linear normalization like this one with some alpha n, mn of course m is the same, minus beta m less or equal to epsilon, and suppose you go to some g at of y, then this is true if and only if, okay, this is true if and only if you have some sort of relation between this guy here, namely an minus 1 alpha m goes to some a, and am minus 1 beta m minus bm go to some b, and g star of y is equal to g of a y minus b. So which means that as soon as you have the process, it doesn't matter how you linearly take, it doesn't matter how the linearization is done, anyway you get the same asymptotic law. And this asymptotic law is one of the three. So this is Kinchin results. It seems to me this is probably the most important reason to get this kind of linearization for UM. Anyway, we take this kind of observable, and okay, so now what we proved. Okay, of course, when we take a dynamical system, any kind of dynamical system, even the nice one, and we compose with, okay, we take this kind of observable, the process which we get is not IID, of course. But one can prove that if you have some sort of mixing condition for the process, which is summarized in these two very famous conditions, famous for people working in this field, which are D1 and D2, or D1, D2, and D prime, basically you can apply all the theory of the IID setting and get the existence of these three famous universal law. And this kind of conditions are mixing conditions, basically. But let me stress, okay, one technical issue. This one, okay, this one is not difficult to get. As soon as the system mixes, even polynomially, this is easy to get in general system. This is a difficult one. Because this is a difficult one, because this must take care of the short returns, point which are close to periodic point, which come back very, very soon, and are very difficult to control only with the curve correlations. But we can handle this if we have the curve correlation against L1 observable for some trick. For this reason, the assumption of L1 is very important at the beginning. Otherwise, it's not completely trivial to get this kind of bound. But in our case, for this kind of noise, observational noise, we did it. And we use some proof, which I already used with other collaborators, to get to make the theory of extreme values for general random transformation. We come back in a moment on the random transformation. Okay, now what I want to show you is a very interesting computation. I mean, very easy but illuminating computation. Because now the question is, you remember, now the idea is to get this which is a sort of, I have to find a linear scaling for because if I find a linear scaling for immediately I have one of the three laws. And the point is, using this kind of observational noise, is the linear scaling comes naturally and is related in a rigorous way to the scaling property of the measure. Rigorous in the sense that I know exactly what the measure is at the finest scale of the noise. And the computation is trivial, because this is the quantity. Here you rewrite this integral here. Now, the only important point is the measure nu can be whatever you want, but theta, which is the measure on the noise, must be Lebesgue, exactly Lebesgue, because not absolutely continuous, but exactly Lebesgue, because I'm using translation invariance and of this measure. And so, if you define this quantity linearly, which is respect to the parameter u in this way, and you define the parameter in this way, I mean just a rewriting of this formula here, you get, you apply dominated convergence theorem, you can do whatever you want, Fubini whatever you want, and you get at the end the result, which is this one. So with this kind of scaling, you get the Gamble law. Well, okay, so what we showed this morning also. And now, why this result is interesting? So we get what we expect to have, namely one of the three laws, because we linearize it. As we should do according to this theory. But important stuff here is we know exactly how the parameter Bm and Im, which are the parameter and the linearization behaves with respect to the property of the observable. And since the observable is related to the measure of the ball, thanks to this identification, we can get exactly how this ball scales. And this is exactly, okay, this is a generation more than one dimension. But let's continue with one dimensions. Okay, okay, I'll come back later. Let me, okay, for instance, look what happens. Okay, first of all, let me see again this formula here. So you see, now what is BM? Because if I know, now the situation is the following. I know I go to this law experimentally because it's what Davide will speak about later on. We have this asymptotic law, so I can check it. The point is, if I am happy and if I put the good BM here, I know the asymptotic limit, what it is. So the point is, what is BM? Let's do the other way around. So we know what I should get. Now the point is, since I know what I should get, can I get some information on BM? And look, the information on BM are here. What is BM? Look, BM is M is a number, right? It's an integer number, but it's the measure of the ball centering the point C with radius epsilon. But here I need to know this measure only for a finite size of epsilon. I have not to go to the limit. I don't have this kind of problem here. So I stop to a finite resolution, and I should know how the measure scales at a finite resolution. Of course, this doesn't give us the local dimension of the measure, which we got in the limit, but still we get something, and this something is rigorous because it's just not in asymptotic limit, but just at a finite size limit. So we can try to use this formula here. How much I have? Okay. So but before going to this measure here, let me tell you something interesting. This formula here can also be obtained using the usual random transformation. So let me say something about this random transformation. In general, random transformation means you have some map which are close to the other. We concatenate, and so we have two sources for the noise in the choice of the points and on the choice of the realizations. And in this case, this process here defines a Markov process is written here, and so we define a stationary measure, which is exactly the measure which I put there. Okay, but the point is we can do the same analysis as before. I mean, a little bit different, but we can get the same scaling for this measure. But this measure, as I told you, is smooth, so we don't get anything new about the local property of this measure. Anyway, this is okay. So let me continue with two other remarks on some particular maps. So I told you before that since we know the asymptotic law, which we could try to get some information on the BM, right? Because BM contains the local property of the measure, but not only. If you remember, BM is just the product between M. M is just an integer number which we have to push to infinity times the size of the noise epsilon. So suppose we are around a point for which, for example, the point spend. I mean, the point doesn't spend too much time to stay around this point here. So in this case, we have to go to a higher value of M in order to get a good statistics. It is exactly what is shown in the next talk about the application of this technique. This happened, for instance, for this map. Okay, this is a very nice map. I mean, it's a smooth map. But the point is the derivative becomes infinity in 0. And this map preserves this measure here. You can check it by inspections. And so if you put a ball around the point -1, this ball scale like epsilon square, because everything, this is a rigorous result, because this is Lebesgue. So in this case, BM is done like this. So if you want to get BM with a good resolution, we have to go to bigger M, because in order to kill epsilon. So it means we can lose statistics from a numerical point of view if we take an observable around this point, -1. It is exactly what Davide saw in the numerical application to temperature records of data. The other example, and this map it should appear sometimes when I spoke. This map is the other way around. So basically, we have points which spend a lot of time around one point, contrary to this one, and we see this behavior in BM also. Okay, this is a map which is sort of intermittent map. Okay, so let me. Okay, this is what experimentally we can do with this kind of technique. Basically, we take some point, and we go to a finite resolution of the noise, and we look at the BM in such a way this BM could contain information about the scaling of the measure of this event around this point at a finite resolution, and this gives us some information on this exponent here, which is related to the fractal dimension of local, but it's not this one because we didn't go to the limit, but still is something related. Okay, if you accept this, and this can anyway is rigorous, but not in the limit, of course, we get good approximation of this number, which was people usually found for local dimension using other kind of technique in the limit. Here instead we look at finite resolutions. And this also can be used in a higher dimension. In this case, we have the competition against this number here, and what is supposed to be the local dimension approximated, and the dimension of the ambient space, which is small d. And let me tell you something to finish about another interesting property, because I thought at the beginning that all this business, I was involved in it because of the relation between recurrence and extreme values. And one can, using this observational noise, get some information about recurrence. For instance, if you take the set Vm, which is a set, which is a ball around the point C of radius C minus um, we can consider what Mark Polkott said this morning. You can consider this kind of process, namely of events, namely we have to look at the first time the point come back to the set itself. Okay, this is okay, and here we don't have any. I don't know. Do we have a point recurrence here? I never thought about this. Surely we don't have cuts because we don't have ergodicity. I never. Probably we have. I mean, I'm not sure. I have to formulate better. Okay, I didn't think about it. Anyway, it doesn't matter because we still have some result. For instance, we can compute exactly this quantity here. So I can compute exactly the statistic of this first return, random first return, provided we take the measure again as the product between the invariant measure and the measure on the noise, because this event here is exactly equal to this one. And for this one, we have already the result, and this is what we get. As Mark showed this morning, we should get something exponential. Of course, we get something exponential, but modulated by the noise, epsilon here. Okay, I stop.
Yes, Sandro. One thing about this idea of adding the noise in the observation. So, to me, what is the added value with respect to considering the end of the second column up to finite size? So that is.
Wait. This one?
Yeah, the last. Yeah, in the sense that my impression is that by doing this observational noise, what you're really doing is taking this mass of points near your Z, and you are diffusing it a bit, and you are regularizing it. But if you go to finite value, which is anyway what you do because you don't take the limit, yes. I mean, what is the difference with respect to the sort of unclear scaling relation that you get in the deterministic case?
Here, it's very
because at finite value, you will always have, if you take the ratio of the mass.
Yeah, but the result is not rigorous. What you get? Not the result. The procedure is not rigorous. The procedure is not rigorous. I mean,
the procedure. What you mean?
The theorem which I stated here.
Ah, okay.
Okay. What I mean, this.
Getting the same.
No. Yes, of course you get the same, but what I'm saying is this result here, this one. Okay, this. Okay, all this. No, this one. Okay, it comes here. This one. All this procedure is rigorous, because you see what I'm doing. I take epsilon, which is fixed, and for instance, you can do the same stuff using the deterministic stuff. Okay, but you have to get a limit inside the integral or outside. Don't remember, because you have to send the radius to 0. And here you don't have to send the radius to 0.
Why do you want to send the radius?
Because if you want to make this procedure rigorous, I mean, if you want to get something, if you want to have an equality here for you have to pass the limits inside. You cannot pass the limit inside because you cannot satisfy the theorem of dominated convergence. Okay, yes. Because the prefactor, again, the measure could disclose to infinity.
But anyway, so somehow the sort of intimate connection you have, correct me if I'm wrong, depends on the fact that you take that the thing is exactly the base.
Absolutely.
Because
Exactly.
basically you are
Exactly.
you are conserving
Yes.
the mass of the points,
Yes.
right?
If you don't take the bag, we have still the same problem. We have to
Yeah,
pass a
of course,
limit
that's-
inside and we are lost.
that's-
This is a very magic stuff which happened here. We have just to use the bag to use the distortion invariance.
You are
of
controlling a singularity.
Yes.
Okay.
Are there other questions?
Questa
Remarks?
stai facendo una diffusione.
This doesn't seem to be the case, so thank you again.
Yeah.